Hi there. So let's go over the April 1st quiz, which covered a number of equilibrium concepts. First question you were asked was to come up with the equilibrium constant expression for the gas phase oxidation of CO, carbon monoxide, to carbon dioxide by means of O2. So what that means is that I've got carbon monoxide and it's reacting with oxygen, and we have an equilibrium, and the product is carbon dioxide. And then we have to go back and see that we have to put a 2 in front of the C in the CO2, and of course everything's in the gas phase. So that part of the problem right there is just translating that phrase right there into a balanced equilibrium reaction. So that might have been the hard part of it. Now, in terms of the equilibrium constant expression, you do the products over the reactants. You raise things to their powers, to their coefficients, raise them to the power of their coefficients. And if it's a Kc, like you were asked to do in this question, if you looked at the answers, that was clear as a Kc. So you do concentration. So the concentration of CO2 will go on the top and it will get squared. And then on the bottom we have the concentration of carbon monoxide. It will get squared. And the concentration of O2 to the first power. That would be a Kc. If we'd done a Kp, then it would be the partial pressure of CO2 squared over the partial pressure of CO squared times the partial pressure of O2 to the first power. All right, let's go ahead and give us more screen here. Second problem, we have a problem here where a compound called COCl2, which is a compound called phosgene. It's introduced at 1 atmosphere pressure, whereupon it dissociates until equilibrium is established, and we have the equilibrium given for us. So we have 2 COCl2 gas, and that equal sign is the equilibrium sign. It makes a solid carbon, which is graphite, so basically carbon like on a pencil lead, and then it makes carbon dioxide, and it makes chlorine gas, like so. Now we're going to make a ICE diagram. So we say ICE, initial change in equilibrium, and we have a column for each thing, and we know this is 1.0 atm. Now since graphite is solid, we don't use it. It's not in the equilibrium at all because we only put gaseous and aqueous things there. And then CO2 and Cl2 are both 0 initially. They don't explicitly say that, but if they don't tell you anything, it gives you a expression. I mean, it's implied. So if we calculated Q for this, that Q would be, CO2 to the first, Cl2 squared over COCl2 squared, and using those conditions, it's 0 times 0 squared over 1 squared. That's 0. That tells us that we've got to go to the product, so plus, minus, and the stoichiometric coefficients here, we multiply x by the coefficients, so 2x, where that 2 is that 2, x, where there's no multiplier because there's nothing in front of the CO there, it's an invisible 1, and then 2x over here for Cl2. So at equilibrium we'll have 1.0 minus 2x, x, and 2x. And if we had the value for K, we could plug these things in and solve it, but really all you were being asked to do is just get this term because this is, as we say, x. So that representation gives us, so the answer would be 1.0 minus 2x, where x is the equilibrium amount of CO2. Setting up an ice chart like that's a key skill, and so that's why we have a question on it like that. All right, so now we have a problem where we've got the equilibrium of nitrogen reacting with hydrogen to give us ammonia. Everything's in the gas phase, and we're asked to get the equilibrium given equilibrium concentrations in moles per liter, right? So that's molarity. So K is going to be equal to NH3 squared, because there's a 2 in front of that NH3 up there, over N2 to the first, which we don't write because there's a 1 that we didn't write up in the equation there, times H2 raised to the power of 3 because there's a coefficient 3 in front of it. So if we put our numbers in here, NH3 is 0.1, so we have 0.10 squared. We have N2 is 0.02, and H2 is 0.01, and that's cubed. So we're going to put those in a calculator, and we have to be careful to make sure we do everything in the right order here. So I have 0.1 squared, divide that by 0.02, and then divide it again by 0.01 cubed, and I get 50,000. And the equilibrium constant doesn't have units. So if you got a different answer from 50,000, you need to check about your math. Again, this is a good thing to practice your use of your calculator with. That is not a trivial part of solving these problems. You've got to be good friends with your calculator. All right, so let's move on to our next one. Our equilibrium now is PCl5 is in equilibrium with PCl3 plus Cl2. Everything's a gas, so I'm just going to leave that out. And what we're told is that initially, well, let's see, we'll make our ice chart here. And let's see what we're told. So we're told it's a 0.250 liter vessel, and initially we have 0.5 moles over 0.250 liters. That's 2 molar, so this is the 2 that goes right there. Presumably we have 0 of these. Q is going to be 0 times 0 over 2. That's 0. Got to be less than K, because K can't be a negative number. And so this is going to be plus X for Cl2 and plus X for PCl3 and minus X for PCl5. So at equilibrium we have 2 minus X molar, X and X. Now what we're told though is at equilibrium we have 0.10 mole, and again that's a 0.250 liter container. That is a 0.40 molar. And we know that that 0.4 molar there is equal to that 2 minus X. So if I say X is equal to 2 minus 0.4, that's 1.6. So that means this is 0.4, this is 1.6, and this is 1.6. So K is going to be 1.6 times 1.6 over 0.4, and again what we got there is the concentration of PCl3 times the concentration of Cl2 over the concentration of PCl5. Nothing has to get raised to any power. And the way we got that 1.6 again was by being given, this equilibrium value there, figuring out what that value was and equating it to the value we came up with in the ice chart in terms of X, and then that gave us the value of X, which gave us the other two terms. So plug this into the calculator. 1.6 squared divided by 0.4. I'm getting 6.4 for that one as my equilibrium constant, and again no units there. All right, next up, are we all the way to the last one? Wow, maybe we're to the last one here. How time flies when you're having fun, huh guys? All right, Equilibrium constant for the reaction 2HI in equilibrium with H2 plus I2, and we're told that that equilibrium constant is 0.49. So 2HI in equilibrium with H2 plus I2, and K is 0.49. Now, what we're going to do initially is put 1 mole of HI in a 1 liter vessel, so 1 mole over 1 liter, that's 1 molar, right? So make our eyes chart. This is 1, these are 0. Q here is going to be 0 times 0 over 1 squared, right? Because K is H squared, H2 concentration to the first power times I2 concentration to the first power divided by HI squared, right? So that's what I've got in my Q there. So Q0, that's less than 0.49, right? That little decision there about what goes here. So that tells us this has got to be plus, this has got to be plus, this has got to be minus. And again, that's not hard to see because H2 and I2 can't become negative. They have to become positive, so they got to go up. We put our x in, and then we multiply the x by the coefficient. So this one becomes 2x. The others 2, we don't write a coefficient there because it's the invisible 1. So at equilibrium, we have 1 minus 2x, x, and x. Now, so what we're going to do at this point is we're going to take that and we're going to plug it into our equation. So we know that K is equal to 0.49. And I'm going to leave a little space here to write the numbers in. The equation for K from this equilibrium is H2 times I2 over HI squared. And so the values we have at equilibrium is x times x, that's H2 and I2, over 1 minus 2x, which we square because we have got a coefficient of 2, right, for HI. Now, this is a quadratic equation. It looks a little threatening, but if we focus on this, we might notice something. 0.49 is equal to x squared over 1 minus 2x quantity squared. So, since we have squares on the top and the bottom of that fraction over there, what we can do is take the square root of both sides, and if we take the square root of both sides, we'll get something that's simpler. So over here, the square root of x squared is x. The square root of 1 minus 2x quantity squared is 1 minus 2x, so that simplifies quite a bit. The square of 0.49, I believe, square root of 0.49 rather, is 0.7. Okay, so now we've got a much simpler equation where x is only in the first power. So we cross multiply. 0.7 times 1 minus 2x is equal to x. And 0.7 times 1 is 0.7. 0.7 times negative 2 is negative 1.4x is equal to x. Now we can add 1.4x to both sides. And we wind up with 0.7 is equal to 2.4x, or x is equal to 0.7 divided by 2.4, and that is, well, let's see, 0.7 divided by 2.4, that comes out to be 0.29. Okay, so what we've got here, this x becomes 0.29. This x becomes 0.29, and then 1 minus 2x is 1 minus 2 times 0.29, and I think that's going to be 0.52. I take that back. That's going to be, that's 29, not 24. It's going to be 0.42 basically. So there's our equilibrium values, so we're asked to calculate the number of moles of hydrogen, which would be the 0.29. That's the answer we've got. Now, we normally want to do a check, and the check is we'll plug in our values and see what Q is. So we have H2 times I2 over HI quantity squared, and what we have there is 0.29 times 0.29 over 0.42 squared. So plugging that in the calculator, I get a Q value of 0.484, which is pretty close to 0.49, so that's okay. We're pretty much at equilibrium. So again, that's some basic equilibrium problem solving skills there. It was a good exercise for you, so you might want to review those before we have our exam.